Today we are doing propensity score matching, which is one of these core 170 type phrases, which feels very verbose, feels very jargony, but is actually kind of cool and kind of interesting once you start to learn about it. Before we get there, let's start the way we try and start every time. Any questions, comments, concerns for the class before we get going? Going once, going twice. All right, so we've been talking about this concept known as identification. It means ruling out alternative explanations. And the idea behind our identifying strategies that we've been talking about has been to find these plausible sources of exogeneity. Remember, endogeneity means determined within the system. Exogeneity means determined outside the system. And basically, when we have stuff that shocks you from outside the system, it allows us to figure out a causal effect. It allows us to figure out the effect of a cause. And there are many reasons for that, but one of the main reasons that we're concerned about is it mitigates this concept of selection bias. When we find plausible exogeneity, we know that selection into the cause is not determined by the system itself. So we saw a bunch of examples of why this might be the case, the woman with the sailboat and so on and so forth. And all these strategies we've been talking about, experiments, diff and diff, regression, instrumentation, regression discontinuity, have helped us to find plausible sources of exogeneity. Today we're going to introduce a new strategy for that called propensity score matching. And the thing about propensity score matching is it's not really plausibly exogenous the way our other identification strategies are. It's more saying, let's take those endogenous factors and use them to our advantage. And to think about that, it's helpful to think about our first identification strategy. Experiments. Remember that with experiments, we often thought we were using what's known as a gold standard in sciences. And it's because we have, fast forwarding to instrumentation, we have this ideal instrument when we experiment, randomization. And with our random assignment in experiments, we can be reasonably convinced that the treatment group looks like the control group. We saw this with the polio vaccine. We've seen it with other experiments. Importantly, with the treatment group looking like the control group, that's true for observable factors, things we can measure like height and weight. But it's also true for unobservable factors, things like how robust you are or how smart you are. Today, with propensity score matching, we're basically trying to mimic that balance you see on experiments without actually experimenting. What does that mean? We're going to group units based on how similar they are, rather than assign units into a treatment or a control. So suppose I think Sweetbriar as a college looks very similar to, say, Randolph-Macon as a college. I'm not randomly assigning a bunch of colleges, some to treatment. We can say the treatment is having a leadership core, and some to control. But I'm comparing units across this treatment, this intervention, by saying ex ante, before the thing, that these two units look very similar, except one is treated and one isn't. And with observable measures, let's go back to our example of the polio vaccine. With observable measures like height and weight, it's really easy to calculate how similar two units are to one another. With a bunch of different observable measures, we can balance similarity along several dimensions. Now, I know this is a lot to throw at you at the beginning of class. We're going to see a bunch of examples which will hopefully make it clear. So remember when we were talking about experimental design, we used the example of Dancing with the Stars. And we wanted to know how watching Dancing with the Stars makes you feel about Nene Leakes. We wanted to know if watching Dancing with the Stars made your subjective, hedonic interpretation of Nene Leakes better or worse. And to do that, we had this made-up experiment where we're going to split people into groups randomly. Some of them are going to watch Dancing with the Stars. Some of them aren't. I don't know why it says donations to a public good. We're going to have people split into random groups. Some of them are watching Dancing with the Stars. Some of them aren't. We thought there might be some additional factors influencing that interpretation, so we're also going to group people by whether they're male or not. And importantly, we're only going to change one factor at a time. This is all review. This is what we did when we were making an experiment. But who remembers how experiments like that could be problematic? What's the problem with that experimental design? Or experimental design in general, perhaps? Because though we think of experimentation as this gold standard, as this ideal way to determine a causal effect, there's a lot of problems with experiments. Who remembers what some of them were? Yeah, Sita.
I know there was talking about groups, like it being difficult to isolate why or if they're doing change because there's so much outside input involved.
Okay, so it might be difficult to isolate that variable that we're interested in. Excellent point. What else? And we don't have to think about the Dancing with the Stars experiment. We can think about experimentation generally. What are some of the shortcomings we've seen to experimentation so far? Yeah, Chloe. Okay, human error, certainly. Building on human error, sometimes, not so much error, but sometimes experimentation is infeasible. Sometimes you just can't run an experiment due to data limitations or funding limitations or what have you. Sometimes you can't run an experiment due to ethical limitations. Sometimes you can't randomly assign subjects to treatment or control. And see, to your point, sometimes with experiments, we might be concerned about what the experiment is doing in itself. If we take a bunch of people, invite them into a lab, and tell them to watch Dancing with the Stars, maybe we're losing some context. Like, you tend to watch Dancing with the Stars with your friends, and that's what's going on. Or maybe you just don't trust the people running the lab, and you have some sort of experimenter bias that's come into play. Though, as leaders who make decisions in a data-driven world, though as leaders we like to think of experimentation as this ideal, it can be problematic. With propensity score matching, what we're doing is trying to simulate an experiment without actually running one. What does that mean? It means rather than assign half of you to watch Dancing with the Stars and half of you to not, we estimate how likely it is that you do watch Dancing with the Stars based on some observable data. And that data can be height and weight, it can be income, it can be any number or information that we can observe to estimate how likely it is that you watch Dancing with the Stars. And this likelihood that you are a Dancing with the Stars viewer, we call a propensity score. Importantly, there might be some of you that, based on your observable data, are quite likely to watch Dancing with the Stars. But for whatever reason, let's call it blind luck, you do not watch Dancing with the Stars. Maybe you're busy Thursdays at 8, 7 Central. Maybe you don't like it. Maybe you have no TV. Whatever the reason, we can have a situation where there are units that have a quite high propensity score. They are very likely to be engaged in the treatment somehow. And Dancing with the Stars is a silly example, but we can think of more important examples, more profound examples, which we'll see later in the class. But don't watch it. Similarly, We might have some of you with a very low propensity score. The likelihood that you are a Dancing with the Stars viewer is quite low, but for whatever reason you watch it anyway. Maybe your best friend watches it. Now that we have these propensity scores, these estimates of how likely you are to be a treated unit, in this case a Dancing with the Stars viewer, and we also have data on whether or not you are a treated unit, whether or not you are a viewer, we can compare people with very similar propensity scores. In other words, we are comparing watched versus didn't watch based on your matched scores. Propensity score matching, that's the identification strategy. We are comparing units based on their propensity scores alone. Questions so far? So one of the things we're doing today is just sort of tying together a bunch of our previous identification strategies. We talked about how propensity score matching kind of simulates experimentation. It also sort of solves one of the problems with regression analysis. Remember, when we were running regressions, we wanted to describe mathematically the data generating process. We wanted to describe systematically how the data look like they do. We had this example of class size influencing test score, and to understand that influence, we had to describe everything that influences test score. And remember, you can ignore that math up there. That's not what's important. The important thing is the concept that what we were trying to do with regression is identify the impact, identify and isolate the impact of one variable. But in order to do that, we needed to describe the data generating process, which is easy to do in the abstract. We say class size influences test score, so does a bunch of other stuff. But in practice, it's very hard to identify and isolate all these factors that influence test score. Not just identify and isolate them, but describe the manner in which they influence test score. So we assume linearity, but that might not be the case. In practice, with regression analysis, what we want to do is describe the data generating process and isolate the impact of one factor. The great thing about propensity score matching is we don't. What causes lung cancer? What do you guys know about lung cancer? Cigarettes, great job. Not a complex question. We all know smoking causes cancer. Obviously, we all know this. But there was a long time where the science wasn't so clear on this. This was not always accepted science. Why is it that smoking causes lung cancer was not always accepted science? What do you guys think? Yeah, Sita.
I mean, yeah, a lot more people used to smoke. It used to be much more commonplace, and it's not that the smoking caused cancer, but that it maybe just helped.
Okay, so smoking was a lot more commonplace, so it sounds like when it's more commonplace, it's hard to isolate the impact, collect good data. Emily D.
I heard some that they thought it was good for them because it was therapeutic and a stress reliever.
Okay, so there are, for purposes of discussion, some benefits to smoking. You know, it might ease your nerves. It might be a bit of a stress relief. Elizabeth. Okay, so similar to Sita's point, like there's sort of a lack of data. It hadn't been thoroughly studied. It's hard to isolate the impact of some variables. Yeah, Cynthia.
Well, there's also the history of it because it's been kind of going on for a lot longer than that. So it's kind of something that becomes tradition. So when you think it's tradition, you don't want to change tradition.
Yeah, so smoking has existed for many, many years. The field of statistics is really only about 110, 150 years old tops. So it's really hard to think about how we worked with data before then when people were still smoking. And to your point, it was tradition. What else? Yeah, Julia. Yeah, we didn't have sophisticated medicine for a long time. We had people dying of cancer much less because they were dying of other things. We didn't have scanners, right? Summing up everything you guys are talking about, it was not always accepted science that smoking caused lung cancer. We saw that some people who smoked were dying, certainly, but there was nothing saying that this correlation was not spurious or that it was not endogenous. People choose to smoke. Selection into smoking is endogenous. Maybe it's correlated with other factors. The association between smoking and lung cancer previously was argued that it was caused by other factors that we might not observe, or it was sensitive to the functional form we chose, or that maybe people who smoked were also more likely to get cancer anyway. Before the science was so definite on smoking causing lung cancer, it was argued, and unfortunately argued correctly, that smoking is endogenous. And remember, what we're doing with these identification strategies is trying to get around this endogeneity problem. So if we want to know the effects of smoking, what should we do? Yeah, see that. Okay, let's look at the data. Great answer. So here's some data comparing smokers to cigarette, or non-smokers to cigarette smokers to cigar and pipe smokers. And we've got it across 3 smoking countries. We've got Canada, the UK, and the US. So just looking at this table, first of all, can everyone see the table okay? This table, which has smoking group and country, and shows the mortality rate per 1,000 person years. What is this table telling you? Who wants to interpret this table for us? Annika, was that a hand or a stretch? All right. Yeah, Elizabeth.
I think it's just saying how many people in that category die per 1,000 person each year.
Yeah, so certainly this table is describing how many people in each of these categories. So a category might be a US-based non-smoker. How many people in each category die per 1,000 people each year? Knowing that the table is saying this, who wants to interpret it for us? Does the table have any patterns? Yeah, Chloe.
Well, it looks like Canada is sort of in with how many people die from such and such things, and then the US is next.
Okay, so Canada looks like it's in the lead of deaths with smokers, but it also looks like it's in the lead of deaths among non-smokers. So maybe it's not smoking. Maybe it's being Canadian that causes people to die. Yeah, Cynthia.
How do they specify the death with this? Is it death specifically related cause or just death in general?
This is just deaths in general. Because it would be pretty rare for a non-smoker to die of a smoking death. But excellent question. So it looks like Canadians are dying more. What else does this table look like? Sita. Cigars and pipes are maybe worse than cigarettes. So before we started class this morning, we all knew that smoking caused lung cancer, and it does. So this table looks kind of weird because if you know anything about cigar smoking or pipe smoking, you don't inhale. Cigarettes you inhale. Cigars and pipes you don't. Yeah, Elizabeth.
I was just going to say that cigar and pipe smokers tend to be much older, so.
Excellent work. You fast-forwarded to the next slide. So, you know that smoking causes lung cancer, but it looks like cigar and pipe smokers have a worse mortality rate, which is interesting because they're not actually bringing any tar into their lungs. And if we think it's the tar in your lungs that causes lung cancer, we wouldn't expect cigar and pipe smokers to have such higher death rates. Now, Elizabeth, now that we're on the next slide, take the lead. What's the difference between cigarettes and pipes? Old people smoke pipes. Young people smoke cigarettes. It's our job to identify sources of bias in the data, sources of endogeneity in the data. One source of bias seems to be age. Juliet, was that a hand or a stretch? Okay.
I know in the case when it comes to cigars, at the very least, another reason that may add up to that is that they have to smoke longer for anything to work compared to the cigarette, which is quick.
Okay. So it's not just how you smoke in terms of mechanically, are you bringing it down or holding it in, but how you smoke in terms of time. And we talked about this in fetal alcohol, right? It's not just how many drinks you have, but how quickly do you drink. And it's much easier to say suck down a whole pack of cigarettes than it is to suck down a whole pouch of pipe tobacco. You need to hold it in longer. It takes longer. What causes lung cancer? We know smoking causes lung cancer, but there's this confounding variable that being old causes people to smoke pipes and cigars more, but also old people have generally higher mortalities. This is not terribly surprising. We know cigar and pipe smokers are typically older than cigarette smokers. And we know that older people die at a higher mortality rate. But this presents a problem for the science because at this point in time, let's say it was 80 years ago or so, we did not know definitively that smoking causes lung cancer. Juliet, to your point from earlier, we didn't have the medical technology, we didn't have scanner tech. Cedar, to your point from earlier, we didn't have as much data. We had much less variation between smokers and non-smokers because there was a lot of smokers. To the scientist's point of view, we could have had a spurious correlation because what we saw in the data were, yeah, people who smoke pipes and cigars are dying more, but they're also older. Now, we already know this from our discussion on DAGs, from our discussion on regression, from our various identification strategies. But the interesting thing here is we're not talking about variable control so much as variable balance. The problem is not that old people smoke cigars. We already knew that. The problem is that young people don't. So we don't have a good way of comparing cigar smokers to cigarette smokers. To put it in a more statsy term, a more mathy term, the distribution of age for each group of smokers is imbalanced. Now, previously, we had conditioned, we had controlled for this balance. Previously, we would run a regression. But the problem with running a regression, and this is just review, we know this from our previous lecture, the problem with running a regression is we only get good regression results when the unobserved factors are independent of X. And again, that's a mathy word, but what it means is that we would expect the outcomes to be the same regardless of age. That was our identifying assumption with regression. Now, in propensity score matching, we're less concerned with control per se and more concerned with balance. And what we have here is a balance plot. Don't worry too much about what it means, but the idea is to get good comparisons, we want, among our treated and comparison group, our treated and control group, those covariates that we're interested, here we have mother's age, but it could just as easily be smoker's age, to look similar across groups. To put it differently, if the outcomes were the same across category, then we would expect the observable characteristics, things like age, things like country of origin, we would expect those to be the same as well. The connection between the independence assumption that we talked about last slide and the characteristics of the group, age, country of origin, etc., is called balance. And if the covariates, these background informations, are similar across group, then we can get a good estimate of what the treatment effect is. If we have an even number of cigar smokers in the young group as we do the old group, then we can rule out the influence that age has. Questions so far? So what do we do? Well, we want to get balance across these groups. Well, Elizabeth, you already hinted at this, but the first thing we have to do is collect those data. We have to get data on age. And yeah, cigar and pipe smokers, on average, are much older than non-smokers and cigarette smokers. So maybe if we want to achieve covariate balance, if we want to balance our comparison across observable data, what we need to do is first collect the data and then, say, divide it into groups. And we might divide those groups into, say, strata. 20 to 40 years old, 40 to 70 years old, and older than 70. The next thing we'll want to do is weight our death rates and adjust them based on our matched ages. What we want to do is calculate not the mortality rate among each smoking group, Canadian cigarette smoker, US pipe smoker. We want to calculate basically a weighted average. We want to calculate the age-specific weight across group relative to the control group, in this case, non-smokers. You'll see that the non-smoking numbers are the same as they were 3 slides ago. And get the age-adjusted mortality rate among groups. And now we see, now that we've adjusted using the 3 age groups we had, now we see that cigarettes have a much higher mortality rate across countries. Suggesting that, yeah, it is bringing the smoke and the tar and all the other chemicals into your lungs that's causing the lung cancer and killing people off. Questions so far? So what we're doing with propensity score matching is we're comparing treated to untreated groups based on their likelihood of entering into a group. We are matching treated to untreated units and comparing their outcomes. Let's see that by way of examples. And let's, for our specific example, talk about endangered species. Beautiful red panda up there. What does it mean for a species to be endangered? Yeah. Okay, so it means there's a limited number. We're concerned about their ability to thrive and survive as a species. But what does it mean to be on the list? Sita. Okay, so there's fewer than X number of them worldwide. Their known population numbers have dipped. Annika, you're environmental sciences. What's the policy implication for that? All right. Juliet, I saw a hand. Did you want to add to that? It's formally recognized. Great point. And that formal recognition makes it illegal to harass an endangered species. When an endangered species is on the list, it is illegal to kill, harm, hunt, or harass that species. No hunting the red panda. Why might we want a list that makes it illegal to kill, harm, harass, or hunt the red panda? What are some benefits? What are some arguments for having this endangered species list? Lily. Okay. If people aren't hunting the red panda, hopefully their species will begin to survive and thrive. Yeah, Riley. It protects biodiversity. What are some arguments against having them on the endangered species list? Yeah, Jackie. I'm sorry, I couldn't hear you. There was a bit of an echo up here. Can you say that again?
So I feel like it was sort of a bit of a cutoff point as well with the endangered species list. So if one day they're taken off, suddenly people can hunt and kill them again. So that the whole thing gets affected.
Okay, so maybe there's a problem with the threshold itself, right? And if a species is just under endangered, it might serve as a perverse incentive to hunt it more. What other arguments are there for not putting these animals on the endangered species list? Yeah, Juliet. Okay. So what I said is we have an endangered species list to protect biodiversity, and that incorporates some of the more esoteric points you all made. The arguments against the endangered species list is maybe it imposes unnecessary costs on society. So Juliet, to your point, maybe if having a panda on the list doesn't actually protect the panda, and it also means we get criminally charged for harassing pandas, not that I'm saying go out and harass pandas, but maybe that's problematic for some reason. To your point more generally, we want to know, does being listed on the endangered species list improve outcomes for these endangered species? Are terrestrial and freshwater vertebrates better off than if they had not been listed? How do we go about answering this question? So just like on Monday, the answer was do a regression discontinuity. And just like last week, the answer was find an instrumental variable. The answer today is use a matching estimator. So the cool thing about this list is there are animals that are very similar to the red panda that for whatever reason don't have to be on the list. We can match species based on any number of observable characteristics, with the treatment being listed as endangered and the control or comparison being not. The basic idea here is we want to collect data on a bunch of different species and classify them according to how similar they are. From there, we calculate a propensity score. How likely are they to be listed as endangered? And we can also look at whether or not they're on the list. The result is you get two groups that look very similar to one another. Sweetbriar looks very similar to Randolph-Macon in a lot of respects. But only we have core 170. With the endangered species list, you implicitly have a list of species that aren't endangered. And we can get two groups that look very similar to one another. Are you a mammal? Are you a fish? Do you live in Southeast Asia? Do you live in temperate climates? We can compare species that on observable data look very similar to one another, the only difference being some are endangered and some are not. And then, now that we have these matched groups, we just compare them. And specifically, we're going to compare groups based on how their status changes. This is something you all said you were interested in. We want to know if we list a species as endangered, does it help it to thrive? Our way of determining whether or not it's thriving in this case is, are they going from endangered to extinct? Hopefully not. Are they going from endangered to not particularly concerning? We want to know, are species that are listed on the endangered species list better off? Are they surviving and thriving more so than they would be had they not been listed? So what do you guys think happens when a species goes on the list? Yeah, Riley. Okay, so their habitat gets more protected. What do you think happens to the species? Do you think they survive and thrive? You would hope so. What about the rest of you? What happens when a species gets listed? Do you think it's better off?
Well, if they're on the list, they tend to get more conservation efforts to help preserve and get the species back on its feet.
Conservation efforts. Excellent point. We'll come back to that in one slide. What about the rest of you? What do you guys think? Does being on the list make a difference? Sita.
Maybe some people are awful and want to go find any remaining members of the species that can keep themselves.
Okay, maybe there's a perverse incentive. Maybe if you're a poacher and all of a sudden you see that the red panda is endangered, you think, I'm going to hunt a bunch more red panda. I'm going to sacrifice those increased criminal risks because their pelts are going to be worth so much more. Interesting. Chloe.
Yeah, that's kind of along the lines of I was going to say that the list should help, but because they are now on the list, there could be some adverse effects that will come upon them.
Yeah, as it turns out, the list doesn't do much. Now, it's not your job to interpret this table, but what they did is basically look at a bunch of different type of matching algorithms. There are a bunch of different ways for making our comparison group. And what they see is maybe there's a negative impact, but it's not statistically significant. There's really no evident help that listing the animals does anything. But Cynthia, you make an excellent point. That's not the whole story. What else comes with being listed as an endangered species? Being listed as an endangered species comes with conservation efforts, both from within the actual criminal act and outside of it. And what we see is that when there are a great deal of conservation efforts made, what it's called here in the table as high funding, being listed as an endangered species helps. When there aren't good conservation efforts made, in this case low funding, it's actually quite detrimental to the species to be listed as endangered. Species recovery is harmed by being listed as endangered without significant governmental and private funding to improve species outcomes. We would want the Endangered Species Act, which makes it illegal to hunt, kill, harass, etc., these animals to protect biodiversity. But without other interventions, it looks like it's not really doing that. And we know this from our matching estimator, from comparing species that look very similar to one another. It's just one happens to be listed and the other doesn't. Questions so far? All right. So what needs to happen in order for this matching estimator to work? What are some of the assumptions we're making here? And here I'm talking about matching in general, not just the Endangered Species Act. Yeah.
Something has to be similar enough that you can use it as an adequate comparison.
Great job. We need similarity. We're basing this comparison on the idea that there can be similar, I'll say species again, but it applies broadly. There can be species that are very likely to be listed as endangered that aren't, and species that are not very likely that are. We need similarities. What else? So yeah, just like with regression, we